Welcome! In this lab, we are faced with a situation where a star is orbiting a black hole with an unknown mass. Given the mass of the star, position data for the star, and the time step for the motion, we can apply Newton's universal gravitational law in order to solve for the mass of the black hole. Because of all the position points gathered for the star over the years, it is easiest to solve for the mass through the use of Python, as doing this by hand would require thousands of iterations of the same calculation. After the code was edited to incorporate dp/dt parallel and dp/dt perpendicular, along with fnet parallel and fnet perpendicular, the mass of the black hole is found to be 2.18 times 10 to the 31st kilogram. Newton's universal law of gravitation is used to extend gravity beyond the Earth. This law shows that all objects attract each other with a force of gravitational attraction. In this equation, g is the gravitational constant, 6.7 times 10 to the negative 11th newtons meter squared per kilogram squared, m1 and m2 are the masses of the two bodies, and then the magnitude of r squared is representative of the distance between the two bodies squared. As shown, the force of gravitational attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance that separates their centers. Looking through the nearly 15,000 position points, it is clear that the positions do not follow any sort of pattern over time, meaning that the star does not maintain a constant velocity. Knowing that the star is in orbit around the black hole, it is easiest to separate the change of velocity into two components, the change of velocity in the perpendicular direction and parallel direction. This concept can then be applied to the change in momentum, as change in momentum is simply the change in velocity times the scalar quantity of the star's mass. As the position data shows that the star has a change of velocity and that it is orbiting around the black hole, it is deduced that dp/dt parallel and dp/dt perpendicular will both have magnitudes greater than 0. This is how we implement these ideas into our Python code. First, I added in a representation of the black hole using the given position and radius. After that, I added the y component of the velocity to match the format of the x component of the velocity. Next, I used the fact that momentum is equal to mass times velocity to edit the final and initial momentum vectors, and then I edited the star's change in velocity and change in momentum using the fact that the change is equal to the final condition minus the initial condition. After that, dp/dt is edited to include the new delta p. Then fnet is edited as the star's velocity times its mass, all divided by delta t, using the fact that fnet equals ma. Note, fnet could also be written as fnet equals dp/dt. Next, we calculate the parallel component of dp/dt, which tells us whether or not the star is speeding up or slowing down, and then dp/dt parallel is equal to the magnitude of dp/dt parallel times p hat, the directional component of the star's momentum. This is found using the code for p hat, which is equal to the final momentum divided by the magnitude of the star's final momentum, and the magnitude of dp/dt, which is equal to the magnitude of the final momentum minus the initial momentum, all divided by delta t. Using the same logic we used for fnet earlier, we can then find fnet parallel, which we know to be equal to the magnitude of the final momentum minus the initial momentum over delta t, all times p hat. After that, perpendicular component of dp/dt is calculated. Typically, dp/dt perpendicular is calculated using the formula for centripetal force, magnitude of the momentum times magnitude of velocity all over the radius. But because we do not know the radius between the black hole and the star, dp/dt perpendicular can be found using the fact that dp/dt is the sum of dp/dt parallel and dp/dt perpendicular. And therefore, dp/dt perpendicular can be calculated by saying it is equal to dp/dt minus dp/dt parallel. Using the same logic for dp/dt perpendicular, fnet perpendicular is calculated to be fnet minus the parallel component of fnet. Then the arrow scale is adjusted so that all the components are represented in the simulation. And finally, a statement is created at the end of the code in order to print out the mass of the black hole. This is accomplished by creating a string that is representative of Newton's universal law of gravitation when one is solving for an unknown mass. In this simulation, the green line represents the path the star travels, the black dot is the black hole, the yellow arrow is fnet, the blue arrow is fnet perpendicular, and the black arrow is fnet parallel. What does it mean? Fnet parallel, fnet perpendicular, and fnet are all different from dp/dt, dp/dt parallel, and dp/dt perpendicular because Newton's second law tells us that fnet is the non-zero total interactions of the surroundings on a system which cause changes to momentum and velocity. dp parallel and dp/dt perpendicular describe effects that must have corresponding causes, which we know to be fnet parallel and fnet perpendicular. We then know if an object is speeding up, it has a dp/dt parallel, and if fnet parallel is not equal to 0. In the same way, if we see that the path of an object is curving, then we know that there is a non-zero dp/dt perpendicular, which is caused by a non-zero fnet perpendicular. What if? Using the components of Newton's universal law of gravitation, we can see that there is no scenario where the mass of the black hole would be different. Newton's universal law of gravitation has 5 components, and as one is a constant g, another the mass of the star, which is not changing, another fnet, which is described by the motion that is also not changing, another the position of the star, which is the same, then there is no way for the 5th component, or the mass of the black hole, to be any different because none of the other components are changing. Using the results of the analysis of our Python code, which were gathered using concepts derived from Newton's universal law of gravitation, it can be concluded that the mass of a black hole at position x equals -4 times 10 to the 10 meters, y equals 3 times 10 to the 10 meters, and z equals 0 meters, that is being orbited by a star of mass 1 times 989 times 10 to the 30 kilograms, is equal to 2. Thanks for watching!